Ready? So, good evening, all of you. Right. So, welcome to UV Physics Academy. So, this is December CSIR batch 2024. Okay, right, fine. So, no more introduction. Let us jump into the subject. So, here we are going to start the first paper. This is quantum mechanics. So, I request you while I am explaining, don't write anything. First, listen, please. After that, I will give you proper time to write everything. Okay, so once you finish, then only I will go to the next concept. So that's why while I'm explaining, please don't write anything, please. So quantum mechanics, right? So what is this quantum mechanics? Why we are studying? What is the use of this quantum mechanics? Why this quantum mechanics was introduced? Hmm? Right. So let us start. At the end of 19th century, at the end of 19th century, okay, so we have physics, of course, there's physics. We have three main branches. Anybody knows what are the main branches at the time? Classical mechanics, electromagnetic theory, quantum mechanics, classical mechanics, electromagnetic theory, and thermodynamics. So these are the three major branches at the time. One is mechanics. Of course, this is the classical mechanics only. And the second part is electromagnetic theory, which is a classical electromagnetic theory. And the third one is thermodynamics. Now, could you please tell me, in this classical mechanics, what you will do? What you will study? Will study about what? Dynamics of matter. Dynamics of matter. For example, I have this pen. This is a mass. It's a material particle. If I throw this with some velocity, it's a pass. I mean, it is moving like one projectile path. Am I right? Okay. So that means you have given some velocity and it is moving under the gravity. So all these motions, that means that motions explained by which mechanics? Classical. So that's why we can say here we are discussing the dynamics of matter or material particles. Cool. Next one. Next one. What is this electromagnetic theory? What is this? Light. Which light? Electromagnetic radiation. Okay. So electromagnetic theory. So here we will study. This is the study of electromagnetic radiation. Radiation, or we can say light. So here we are studying the properties of radiation or light. And what this thermodynamics is doing. For example, you have taken this body. What body it is? Let us say black body. So now here is a light. So this black body absorbs the light or a radiation. And once you heat that black body, the energy will be emitted. So all these things can be explained by, okay, at that times, that means a macroscopic point of view. Right. So here, this will discuss the relation between matter and radiation. Fine. So then people thought that this is the complete physics. So this is called classical physics. And they announced physics is completed. Once we think it is completed, then only it is the beginning actually. So then problem started. What problem started? So later they faced two major troubles. So that is later faced two major problems. Anybody knows what are those? One is a microscopic phenomenon, microscopic properties. Another is a relativistic. Another is a relativistic. These two major issues came. So these two major issues were not explained by this classical physics. Then they thought we need another new mechanics. So that is nothing but quantum. That's it. So this is the way to quantum mechanics. So everybody thought this is the end of physics because everything is explained now. So if you see surrounded by you, what you are seeing? What are there? What you have in this classroom? Fans, benches. You forgot about you. You, okay? Benches, fans, inga light. Lights, light. So you have only two things in this nature. One is a matter, another is a radiation. So that's why this whole nature contains only two things. One is matter, another is radiation. That's why always matter will convert it to radiation and radiation converted to matter. Can you please tell me what are the examples for that? Matter converted to radiation. What is the example? Matter to radiation. Matter to radiation or radiation to matter. I hope you have heard about this pair production. Pair production. What is this pair production? Gamma split into electron and a positron. What is a gamma? What is electron and positron? So radiation is converted to matter. Next, what is matter to radiation? Pair annihilation. Annihilation. So electron and positron combine together. What you will get? Radiation. Gamma. So that's why in this nature only two things. One is our matter, another is a radiation. Okay, so let us start and come on, start. I'll give the time, so please write properly, no problem. But don't write while I'm explaining. Please listen what I'm explaining, please. So two major problems. One is a microscopic domain, another is a relativistic domain. So these two domains are not explained by this classical physics. Right, ready? Right, now let us see. So how these two problems is over? Have you written? Right. So how these two problems overcome by this quantum mechanics? Now ready, start. So in 1900, so there was one a beautiful theory. Anybody knows what is that? Max Planck quantum theory of radiation. Quantum theory of radiation. Yes. Can anybody please say what is this quantum theory of radiation? Hmm? Listen. For example, you have a black body. Now onwards, listen carefully, please. Now you have a black body. Now this is absorbing the energy. How much energy is absorbing? H? Okay. That means what you are saying is whenever you have an electron like this, and if it wants to excite, okay, to the higher state, it will absorb the energy. Say yes or no? Yes, sir. Right? And similarly, whenever it is coming to the ground state, again it will release the energy. So this energy is, let us say, delta E, and this is also delta E. So according to Max Planck quantum theory of radiation, this delta E, either absorption or emission, this is equal to NH nu. That means integral multiple of H nu. This is what you are saying. Say yes or no? Yes. Who told you it is integral multiple? Max Planck? Einstein? How do you know it is integral multiple? First of all, what is meant by integral multiple? Multiple of 1, 2, 3. But not multiple of 1 by 2, 2 by 3, 3 by 4. That means no fractions. Only integral values. Say yes or no? How many students are here? You will say 50 and off, 70 and off. What you will say? 70, 80, 100, like that. Am I right? That is the integer. How many chairs are there? How many benches are there? So that is what? A number. So what you are saying is this n is integer. Integer or integral. Integral values. Correct. It takes only integral values. What is the meaning of integral values? 1, 2, 3. How do you know? Okay. I think this was studied in a BSc, I think. Maybe your BScs are explained E equal to NH nu, where n is the integer. Always it takes energy in the integral multiple of H nu. That means it takes H nu, 2H nu, 3H nu. But it won't take H nu by 2, H nu by 3, it won't take. Am I right? Then did you ask, sir, why it is integer, why it can't fraction? What they will say, you will understand in MSc. You will understand in MSc they will explain very well. That's why they escaped. In MSc, bad luck, Corona came. Okay, so anyhow, that's why they didn't explain. Ready. Now the point is, why it is integral values? Why it is taking integral values? Shall we discuss? Are you ready? Yes, right. So for this, I'm going to take the paper published by this Max Planck. Let me take a oscillator called Planck's oscillator. So till now you have studied, I think the minimum amount of energy is what? H nu. Why minimum amount of energy is H nu? That means n is always integer. Why n is always integer? Why it can't be half integral? Why it can't be half integral? So let us discuss. It's quite interesting. Ready. So here I am taking this Planck's oscillator. Planck's oscillator means no need to get tension. It's just like a harmonic oscillator. So this is the mass m and this is a force constant k. I hope you know k is nothing but what? M omega square. Right? Now this is the mean position. Let us say from the mean position it is displaced through a displacement x. If it is a displaced like this, due to the restoring force, it will come back. Say yes or no? Yes, right? So this is the restoring force and coming back. So this is the displacement and this is coming. That means velocity direction. Say yes or no? Yes. That's why acceleration is directly proportional to this is the displacement. Then this is the velocity. Then acceleration is directly proportional to minus x. అదే కదా హార్మోనిక్ ఆసిలేటర్ అంటే SHM. వాట్ ఈజ్ SHM? Acceleration. It's a periodic motion whose acceleration is directly proportional to minus x. Fan. The fan is rotating. Is it a periodic motion? Fan is a periodic motion? Yes. Is it a harmonic motion? No. All periodic motions are not harmonic motions. In the 8th class you studied. All harmonic motions are periodic motions. Harmonic motion means it's a periodic motion, to and fro motion or periodic motion whose acceleration is proportional to minus x. Fan is a periodic motion, but acceleration is not proportional to minus x. Cool. So that's why we can say acceleration is proportional to minus x. That's why this is a SHM. Now, I'm going to write its energy. The total energy is nothing but kinetic energy plus potential energy. When I ask the question, then only speak. P square by 2m and this potential energy is a half k x square. K is nothing but m omega square x square. So that's the total energy. Now what I'm going to do is, I'm taking this total energy again one more time. P square by 2m plus a half m omega square x square. So I request you please divide this entire thing with e. P square by 2me plus half m omega square x square by e is equal to how much? 1. Now I would like to rewrite this. X square, observe carefully. I think this can be written as 2e by m omega square under root whole square. Shall I? Shall I? Plus p square by, this is a 2me under root 2me whole square equal to 1. So I think you got this is nothing but x square by a square plus y square by b square equal to 1. So this represents equation of ellipse. Oh, nice. So once again, what we are discussing, according to Planck's theory of radiation, the amount of energy absorbed or the amount of energy released is always integral multiple of h in. So here we are discussing why it is integer, why it is integral all values only, why it is taking integral values only, why it can't take half. Is it clear? So in that, how we started, please observe carefully. So this is oscillator, displacement, velocity, acceleration, and this is the total energy expression. Just I divide the entire equation with e, I got that 1, and after that just I have written root whole square, that's it, and finally I got a ellipse equation. So what is this x? Position. What is this p? Moment. If I draw a graph in xp coordinates, then it looks like a ellipse. So what is that xp coordinate system? Phase space. What is that? See, if you really not heard about these words, that means your MSc is incomplete. Whatever the words I am using here, if you didn't listen anywhere in your 2 years course, means your MSc is incomplete. What is the word I used here? Phase space. Phase space is the combination of, at least you must remember now, phase space is the combination of position and momentum. Only position, real space. Okay, so position and momentum together is called phase space. Now tell me, if this is the harmonic oscillator, this is the spring and the harmonic oscillator, you displace it and it's moving back. Say yes or no? So how it is moving? Like this. Which space it is? Hey, this space. You are seeing na? Is it a real? Am I real man? This is a real pen. So you are watching na? So which space? So this is the real space motion. Okay. If you represent this motion in phase space, in the real space, oscillator is like this, simple pendulum is like this. But if you represent its motion in phase space, it looks like a L. So this motion in the real space is converted to or is replaced by which motion? Elliptical path. It moves in elliptical path. This was the CSIR question. Trajectory of harmonic oscillator in phase space. What is the trajectory? Listen carefully and don't see the board and write yourself. If you listen carefully, you need not to see the board. Meanwhile, in between you can see, but algebra don't see, please. So this was the previous CSIR question, the trajectory. This is the trajectory of oscillator in phase space. Komal Pradhamesh Sohale. Please check whether your camera is coming or not, Babu. See, now also I can say simply energy is NH nu. But when you will know why it is always integer, why it is taking integral values. Okay, so this is your last class, I think, that means coaching class, you must know. So finally, the motion of harmonic oscillator in the real space is a to and fro motion. What is the motion called? To and fro motion. But if you represent that motion in the phase space, it looks like a elliptical path. Ready? Is it over? Over. Right. Now ready. So this is what we get, ellipse. Okay. So now I have drawn this elliptical path. In CSI they ask this question. There are two ellipses in the option. One is a clockwise ellipse, another is the anti-clockwise ellipse. Ayyo, sir said in the class only ellipse, but in the exam they asked clockwise. That means arrow marks are clockwise. Another option is anti-clockwise. Now tell me, clock or anti-clock? So I will give you a small hint. Now this is the displacement towards right or left? Right. Then it is moving back. That means its velocity is backward. Say yes or no? Yes. Velocity backward means momentum is also back. So displacement is forward. Displacement is forward. Then velocity is backward. I'm giving you 1 minute time. Please think. Now it is a clock or anti-clock. Why?
X is moving forward in this direction and momentum is in the backward. So it is in the anti-clockwise direction.
So this is the mean position. Displacement is a forward and momentum is backward. That's why it is anti-clockwise direction. This is what you are saying. Anti-clockwise. You you think about it or simply you are saying the answer? Okay. Here, anti-clockwise. Anti-clockwise. When a question asks, stand and say the answer. Anti-clockwise. Clockwise. Why? If a body is moved backward, that means if the mass is compressed like this is called extension actually. If you push like this, okay, this is a pulling, right? So if you push like this, then momentum will be in that direction, opposite. Always displacement and momentum will be opposite direction. If you pull it, it will move back. If you push it, it will come forward. That is a harmonic motion. Say yes or no? Right. Why it is clockwise? We'll try online students. Anyone wants to say the answer? No one is ready to say the answer. Sit down. Next. Anti-clockwise. Next. Why?
It's moving in forward direction. So first mean position to X value increases
Yes.
and simultaneously momentum backward direction means momentum decreases. So if you draw the graphic first quadrant, then position increases and momentum decreases.
I didn't understand why if a position is increasing, momentum is decreasing.
Momentum is in opposite direction.
No, you didn't understand properly. See, this is the main problem with you. Sit down. Did you understand what is meant by harmonic motion first of all? Right. If this is the mass, let us say spring is here. Now this is the mean position. At this point, its position is 0, let us suppose. What is its velocity? 0. It is at rest. Now you displace like this. Okay? And the displacement is positive or negative? Positive. And you released. Then it is moving back. It's moving back, moving. How momentum is decreasing? Momentum is not decreasing. Momentum is increasing in the negative direction. So, if this is the mass initially, if you displace like this, you said anti-clockwise, means it's going like this, then momentum is positive or negative? But momentum is negative. Simple thing. See, what is this harmonic oscillator? If x is a positive, its momentum is negative, and vice versa. X is a negative, momentum is positive. So this is SHM. So if you have this particle at the mean position, displace, x is a positive, and you released it, then momentum should be negative. If you go in the anti-clockwise direction, momentum is positive. So that's why the trajectory should be clock or anti-clock. So in this clockwise only, if x is a positive, momentum is a negative. Sir, I want to push it back. That means this is the mass, let us suppose. Now you displace it like this. That means displacement is backward. So negative or positive? Negative. And you release it. Momentum is then you please take the pen and do like this, then only you will feel that. So otherwise simply whatever I'm doing that acting, you won't feel. If you do it yourself, then only you will understand. One more time. If this is the main position, displaced and released, then in which direction it is moving? Backward. Backward means momentum. So position positive, momentum negative, which quadrant? Fourth quadrant. So that's why it should start from which quadrant? Fourth quadrant. So starts from fourth quadrant means clock or anti-clock? Clock. Next one. If this is here, you pushed it. That means you moved it back. That backward motion. So x is negative. If x is a negative, right. Now x is a negative, you released it. The x negative means momentum must be positive. Positive means up or down? Because x, then momentum should be positive. X negative, momentum positive, which quadrant? So that's why it starts from second quadrant. So like that. So always whether it is a pushing or pulling, whatever it is, always it moves in clockwise. That's it. This was the previous CSIR question. Right. Now come back to our story. Now here what we are discussing is why that amount of energy absorbed. Do you understand what is this? Which diagram it is? Phase space diagram. Educational system, leave it. Okay, fine. Now again I am taking this elliptical path. This is x and this is a p. And now here just what I am doing is I am just dividing into small cells called unit cells. Unit cells. Now I am taking this one unit cell. Observe carefully. To understand one point, how much time we are spending, that is physics. That's why it is very difficult. To say it's simple, it is always integral multiple of h and u. But to show that how many things we have to discuss. Ready? So I have taken this one unit cell. Can you please tell me what is this length? Shall I take it as a delta x? Because this is along x-axis. and I am taking this as a momentum, that's why I am taking it as a delta Px. Delta Px. Now, so this is called a unit cell. This is the unit cell, or one more word is there, microstate. Hmm. Microstate. The state where the particle is occupying is called microstate. So where you sit, that position is called microstate. Then what is a macrostate? Abba? The macrostate for this bench is 3 2. What is that? 3 2. The macrostate for that bench is 3 3. Now tell me what is macrostate? That is the energy level. This is the energy level. Here how many particles? Here how many particles? That 3 comma 2 is called macrostate. Okay, and the positions where they are sitting, that occupying, is called a microstate. Okay, so this is the microstate. Okay, fine. Now I would like to find what is the area of unit cell. I hope you know it's a 2 dimension, x and px, length into width. What is the length here? Delta x. What is the width here? Delta px. Could you please tell me what is delta x into delta px? What is delta x into delta p? It's a Planck's constant. He taken as a Planck's constant h. The smallest available area. If it is a 3 dimension, smallest available volume. That's why it is called unit cell. Unit cell means the smallest available volume in 3 dimension. So in 2 dimension also we can say. Is that clear? Right. So what is the area of unit cell here? Delta x into delta x. How much it is? H. Not h cross, only h I have taken. Okay. Now, ready. Listen carefully, please. Next, second thing, I am taking this as a small a. Small a is the area of unit cell. Second one, I am taking total area. Observe carefully, these are not in the books. Total area. What is the shape of this diagram? Ellipse. What is the area of the ellipse? Ellipse area, area of ellipse. Next. Next. Pi AB. 4/3 pi r cube, volume of the sphere. Pi AB, not this one, pi AB. Okay, so because this is the ellipse, x square by a square plus y square by b square equal to 1. Then what is the area of the ellipse? Pi AB. Now again come back. Can you please tell me what is the a here? A is nothing but under root. What is a b? Under root. Okay, now observe carefully. So I am taking the total area capital A, pi into what is AMA? Under root 2e by m omega square into B under root 2me. Now what is this? M and m gets cancelled. Okay, right? Now how much it is? Pi as it is. Root 2. 2. Root e e by omega, because under root omega square is nothing but what? Omega. So could you please tell me what is the total area I got? What is the area of unit cell? Area of unit cell. What is the area of total phase space here? Now tell me. For example, I have this, let us suppose this surface is there like this one. Okay, Let us say this is some area. Now I have this unit cell. Now I am placing the unit cell like this, okay. So the total space I am keeping these unit cells, understand. Now I want to find how many number of unit cells are there. How? That's it. The total area divided by area of, that's good, that's good. Now tell me, now I want to find number of unit cells. Now this is the total area, this much. Each cell area is H. Now how many number of cells are there? Total area by area of unit cell. What is the total area? 2 pi E by then 2 pi E by H omega. Bring that 2 pi to denominator. H by 2 pi H cross. Then E by H cross omega. N equal to E by H cross omega. E equal to NH cross omega. That's the derivation. We are saying simply E equal to NH omega, NH nu is also nothing but H cross omega. Do you understand? 1 minute. Let me. So what I am saying is, once you got that total area is 2 pi E by omega, and the area of unit cell is H, then the number of unit cells, is nothing but total area by A. So that is a 2 pi E by omega H. So this is the number of unit cells. What is this? Number of unit cells. It's a counting number. Say yes or no? Yes. Counting number. Or simply number. Okay. So this is a n equal to 2 pi E by H omega. Now just bring this 2 pi to the denominator. Then it is n equal to E by H cross omega. So E equal to NH cross omega. Now tell me, what is this n? In this derivation, what is n? You are not saying anything, means you are not involved in the class. After 2 days you will go home. N is what in this class? That number of unit cells. Will you say 100 and off, 20 and off, 50 and off? What you will say? Exact integral value. That's why in this derivation that n is nothing but number of unit cells. So that number is always integral. We never say the number of people, number of items, number of chairs, whatever it is. We never say half integral. Always we will say integral. So that's why n is always clear. Don't write while I am explaining. Last and final warning. Don't write while I am explaining. After the explanation, please write. I will. So this is nothing but 2 pi E by omega. If you are copying everything, no use. You have to write yourself. Then only you will get confidence. Observation, thinking, and remembering and writing. Observation, thinking, remembering, and writing on the notes. While I am explaining, if you write, no use. So after that, you just divide these two to get the n number. That means this n equal to the total area by small a. Online students, please be serious. My humble request, please listen carefully and write later, please. While you are writing in your notebook, please imagine you are explaining to someone and explain. Then you will remember and you will get confidence. I think you can do that simplification yourself. So this n is always integral. Integral value. It takes only integral value. Right. Now up to this, if you have any doubt, please ask. So this was the Planck's oscillator. And have you read this book, H.E. White? Have you seen that book? Okay. The first page is this only. That is an atomic and molecular spectroscopy book, H.E. White. So if you open that first book, first page, you will be having this oscillator. Because atomic spectroscopy is what? Absorption of energy, emission of energy, spectra. So that's the first discussion is about Planck's oscillator. Yes, any doubts, please ask. In this.
So when we divide the ellipse into multiple unit cells, it's not always necessary that all of the area is divided into exact unit cells. Right? So then,
What is our question? Every year one student will ask this question. Her question is this one. I think you also got the doubt, but you are not asking. Okay. So our question is, it's a valid question. So our question is, you have divided this. Okay. So like this you have divided. Okay. So what about these corners? I think that's your doubt, right? Now I want to ask one thing. What is the limit of position? Limits of position. From where to where? Position limits. Minus infinity to plus infinity. Momentum limits. Minus infinity to plus. So phase space is not only this up to this. It's an infinite space. And then why you have drawn only one elliptical path? One elliptical path represent one energy, ground state energy. First excited, another ellipse. Second excited, another ellipse. Like that, how many energy levels are there? Infinite. So whenever there is infinite number of space is there, infinite space is there, whatever you are dividing is also infinite number. That's why we need not to bother about these corners. Okay, understand? That's not a 10 or 15 or 20. It is what? Infinite. That's why there was one question in the just exam. Shall I ask? The answer is in my discussion. Till now, 2 minutes I am discussing something. What I discussed one more time I am saying. Position limits are from minus infinity to plus infinity. Amma, you have to listen carefully because till yesterday your life is very different and today onwards it's very different. Okay, till yesterday you don't have this habit of sitting on the benches and someone is speaking and listening. You are simply, there is no that type of habit. Now it's completely different. So please focus. Whatever I am saying is a very crucial, very important. So position is minus infinity to plus infinity and momentum is also minus infinity to plus infinity. So that's why it's a phase space is an infinite space, first thing. Next, then why you have drawn only that ellipse? Each elliptical path represent state of the system. Let us say ground state. First excited, another energy. Second excited, another energy. Is that clear? Now the question is, listen. Ready? The question is, what is the difference between the areas of two ellipses? What is the difference in the, difference between the areas of two elliptical paths in phase space of harmonic oscillator? H cross omega. That was the question. Because each ellipse is what? One state. Let us say ground state. What is the ground state? H cross omega. First excited, ground state, half H cross omega. First excited state, 3 by 2 H cross omega. Next, 5 by 2 H cross omega. So what is the energy difference? H cross omega, H cross omega. So that was the question. I hope you understand, right? Right. You can next. Ready? Right. So that was the story of 1900. So how many years back we went? This is 2024. That is 1900. What we are doing Indians in 1900? We are fighting with Katlu Katarlu. So they are doing these things. Okay. Next, 1905. What happened? Einstein photoelectric effect. This is the beautiful thing. Right. All of you listen carefully, please. Einstein's photoelectric effect. So it's a beautiful phenomena and it's amazing. Okay, and genius how he got the ideas that I will also share with you. So please listen carefully. So what is the problem with this photoelectric effect? Till then, I mean in 1600, if you go to 1605, 1604, there were two people. One is a Newton, another is Hooke, I think. Hooke, the something. Okay, anyhow. So these two people are fighting. What? Newton say light is particle. Light behaves like a particle. Another person will say maybe in your textbooks it is Huygens, but not Huygens, right? So another person will say light behaves like a wave. So finally, after so many experiments, they decided yes, light behaves like a wave. After that, we got Maxwell's equations, that electromagnetic wave equations, everything. Okay, fine. Now, what is this photoelectric effect? This is a beautiful phenomena. All of you, please listen carefully. Photoelectric effect. What is this? Now, for example, I have a metal plate. Let us say this is the metal plate, zinc, platinum, or sodium, whatever it is, some metal plate here. Now, here there is a light. So, this light is irradiated with this. That means that light falls on the surface. It's coming like this, right? It strikes the surface, and this is having some free electrons, let us say, okay, whatever it is, some electrons are there, and those electrons are ejected. So ejection of electrons from the metal surface when it is irradiated with electromagnetic radiation, like which wave? Which light you will get this phenomena? UV light, right? So for UV light you will observe this. Okay, fine. Anyhow, so one more time, when light falls on the metal surface, the electrons will be emitted or ejected. So this phenomena is nothing but what? Photoelectric. Cool, fine. I think in your BSc you have studied all these things, am I right? Okay. So now here I have some electrons. Now what I am doing is, I am sending some light. All of you listen carefully, of certain frequency or certain intensity, whatever it is, and the electrons are ejected with some kinetic energy. Now this phenomena we have to explain. How we are getting this? Don't send any messages, I won't see. Okay, so I won't see your messages. Don't waste your time, please. Right, ready. Now, so here what is happening? The electrons are emitted. So when a metal plate or metal surface is irradiated, irradiated by electromagnetic radiation, then what will happen? The electrons will be emitted. Say yes or no. What are those electrons called? Photoelectrons. Photoelectrons. Electrons will be emitted. Right. So at that time, the people are thinking the light behaves like a wave. This was approved. That means by after Maxwell's equations, everything they agreed. The light behaves like a wave. So here the problem started. Now let us discuss. Okay. Now first I am assuming a light as a wave. I am assuming like this. So all of you please listen. Now here I have taken this metal surface. These are not in the books. Please listen. I am sending this light. Now the light behaves like a wave. Whenever you are talking about a wave, it is having intensity. Say yes or no? Yes. Right. So intensity is directly proportional to what? Amplitude square. Similarly, energy is also proportional to what? Amplitude square. If you assume light behaves like a wave, then if you are sending the light, that light is having certain intensity. So intensity is proportional to amplitude square. Similarly, energy is also proportional to amplitude square. Cool. That means what? If you send with high intensity, you are sending with a high energy. Say yes or no? Yes. Good. Now listen. Okay. So what happened? If it behaves like a wave, intensity is proportional to amplitude square and energy is also proportional to amplitude square. So more intensity means more energy. So if you are sending high intensity light, means you are sending high energy light. If the sending is high energy light, the electron also should have more kinetic energy or less kinetic energy? You understand this point? If light is a wave, are you understanding what I am saying? If light behaves like a wave, purely wave behavior, then you are sending with a high intensity light, means you are sending high energy. Say yes or no? If you are sending high energy, the electron must go with high kinetic energy. If light behaves like a wave, you will accept it or not? Good. So first point, if intensity increases, okay, energy of light increases, and the kinetic energy of electron, the kinetic energy of electron also increases. So that means what you are saying is the kinetic energy of electron increases with intensity. But experimentally what they found? Kinetic energy of the electron is independent of intensity. So contradiction. I don't know how many of you are listening properly. If you assume it behaves like a wave, if you increase the intensity, then definitely electron must have high kinetic energy. If low intensity, low energy, low kinetic energy. So the kinetic energy of the ejected electron must vary with intensity. This is all happens if you assume the light behaves like a wave. What the point? So, contradiction. I can't write all the words, just if you listen carefully, you will understand. Contradiction to experiment result. So, experimentally, what they found? Kinetic energy is super. Kinetic energy of electron is super. Independent of intensity. Independent of intensity of light. Sorry. Yeah, the board is not visible. Okay, so I am writing here the conclusion. What is the contradiction? Don't write while I am explaining. Please. నేను అలా చెప్తూనే ఉంటాను, వాళ్ళు అలా రాసుకుంటూనే ఉంటారు. ఏం చేయాలి? Contradiction. What is that? Kinetic energy of electron is independent of super. So the point is ruled out. What is that? Light is not behaving like a wave. If you assume light is behaving like a wave, it must satisfy this condition. If you increase the intensity, kinetic energy, because you are sending high energy, so definitely the ejected electron must have high kinetic. But that is not they observe. What they observe? Kinetic energy of the electron independent of intensity of the light. Okay, okay. First write down. Listen carefully what I am explaining, what are the points I am explaining, listen carefully please. So if you consider the wave nature, what it is violating? It is violating the observation of kinetic energy. Kinetic energy observation it is violating. Experimentally what we find? Whatever may be the intensity, the kinetic energy of electron remains same. It is independent of intensity. But if you assume it is a wave, As intensity increases, energy of the wave is increasing. That's why kinetic energy of the electron must be increased. But it is not happening like this. Is it clear? 2 points are very beautiful points. The first point is over. The second point. Ready? Over? Is it completed? So, come and tell me. So, what did you understand? Why we can't take light behaves like a wave here? If you take light behaves like a wave, what's the problem? What is the contradiction you got? Please explain. What do you understand?
As radiated wave has high intensity, then it must be emitted with high kinetic energy.
Who is emitting?
Electrons must be emitted with high kinetic energy, but contradiction to this, that kinetic energy of electron is not high and it is independent
It
of.
is not changing with respect to that intensity. What they observed, right? Very good. Sit down. So right. Now once again. So first point, whenever you have taken this electron, see, super, right? Now here you have taken a wave behavior. Listen carefully. Then what's the problem? If you increase the intensity of the wave, the electrons must be emitted with high kinetic energy, but that is not observed. So that's why what's happening here? Wait, we'll discuss. Now for example, let us suppose this is the metal plate. Okay, right, this is the metal plate. Now you are sending light. Now if you increase the intensity, then also kinetic energy is not increased. What is the meaning of that? That means the electrons are not taking that light as a whole wave. I don't know how many of you understand. One more time. The electrons are not taking that wave energy as a whole. Still not understand. If the electrons are taking that wave energy, whatever you are sending as a whole, then definitely kinetic energy must be increased. What is the meaning of that? Why kinetic energy is not increasing? Simple. They are not taking it as a whole. I will give you one example. Now here I kept a stone. Okay, let us say on my head. Let us suppose. So here is a stone. Okay. Now what you are sending is you are you are throwing some stones. You are throwing some stones, and you are throwing some water pipe. You know, water pipe. So you are using the water pipe. There is a stone, and you want to hit that stone. You are using two cases. One is water pipe. Water pipe means what? The water will go as a whole. Say yes or no. Next, you are having some stones in your hand, and you are throwing the stones like this, or you are throwing the stones like this. Then what happened? That the stones are coming individually, and they will go and hit the stone. First case is as a whole. Second case is individual. So you want to understand. That's why I have given that example. Now in this case, what is happening? The electrons which are inside the metal, if you are sending a light as a wave, they are not accepting that energy as a whole wave. Say yes or no? Yes. That's why the kinetic energy is not increasing. Then people explain, okay, so what's happening here? Whenever, very important, whenever the photon is hitting the target, while it is hitting the target, it is placing some discrete amount of energies at different places. Oh, what is this? Electron is not accepting the whole energy as a wave. Once the light is striking the metal plate, while it is hitting the metal plate, that is placing some, or that is giving some what energies? Discrete energies at different sites or different locations. What is the meaning of that? Giving a discrete energy. That discrete energy going and hitting the electron. Say yes or no? So one discrete energy will hit one particle. Second example I told you. You are having some stones. You are throwing the stones like this. One of the stone will hit her, all the stones will hit her. That's it. That's why it is a one-to-one interaction. That is the particle behavior. Particle behavior means what? Particle collision. Particle collision means what? If you have one particle, if you throw the another particle, it will go and hit only one particle or 100 particles at a time. So that's why the photoelectric effect is not one to many. The photoelectric effect is one to one. One more time. The light is coming and falling on the surface. Whenever it is hitting the surface, it is giving what kind of energy? Discrete amount of energy. That means now it behaves like a good. That discrete amount of energy is absorbed by how many photons? So, how many electrons? One discrete energy is absorbed by one electron. That's why it is a one-to-one interaction. Is it clear? This point is clear? So finally, what do you understand? While it is hitting the target, it is giving. That means in the form of discrete amount of energy it is giving. That means it is behaving like a. Wait. So what's the observation? Electron is not absorbing. Very good. Absorbing the energy as a whole. Whole spelling? As a whole wave. Is it okay? Maybe my English is not that much good, but you understand. Okay, right. So electron is not absorbing the energy which you are sending. It is not absorbing like a. ఏదో సెంటెన్స్ రాంగ్ ఉన్నట్టుందమ్మా. ఓకే, is not absorbing the energy of a wave as a whole. Okay, సర్లే, not absorbing the energy. Understand, whole energy. Okay, okay, thank you. Absorbing whole energy of the wave. Okay, it's not absorbing the whole energy of the wave. That's why the energy, kinetic energy of the electron is not increased. Then the people explain, okay, Bhaiya, so how it is absorbing? Simple, they simply changed. What they changed? While it is hitting the target, it is placing some discrete amount of energies. That discrete amount of energies are absorbed by photon. Electron. One electron will absorb only. That's good. So, while hitting the target, okay, light gives discrete energies, discrete amount of energy, okay, at different locations. Okay, super. That means here what is happening, this discrete amount of energy is absorbed by one electron. That's why this is a 1-to-1 interaction. Repeat. 1-to-1 interaction. So only one photon is absorbed by one electron. That's the meaning of the sentence. So one photon and one electron. Super. Now ready. So now you said while it is hitting, it is behaving like a, okay na? Right. So this indicates which behavior? Particle behavior. Right. Right. Now let us discuss about the second point. Now you concluded it is having the particle behavior. Super. The particle behavior. Now listen, Amma, this is very interesting. Okay, so again here we have electrons. Are you listening? Yes, sir. Here electrons. Now what you said, while it is hitting the target, it's not a wave, it is giving some discrete amount of energy. And that energy is absorbed by one electron and it is coming. Say yes or no? Yes, sir. Now ready. Now again what I am doing is, I am increasing the intensity of this. Still I don't know whether it is wave or particle, I don't know. Again what I am doing? Increasing the intensity. Good. Now this is the most important point. While it is hitting, it behaves like a particle. Cool. Now I increased the intensity. If I increase the intensity, then what will happen? Wait. Then also, because now light behaves like a, although increase the intensity, is there any many one interaction or one many interaction? Again. So if you increase the intensity, then also 1-to-1 interaction. So there should not be any change in the number of electrons emitted. Say yes or no? Not understand. నేను ఏదో అరుస్తున్నట్టున్నాను మళ్ళీ ఇంకోసారి. Now you concluded, జాగ్రత్తగా వినండి, very important, it's beautiful. That genius, how he got that idea, we don't know. So one more time. Actually what I am saying is from their, what they have written, I am explaining those things, not from the books. Listen. So Once again, while it is hitting the target, it behaves like a particle because it is giving a discrete amount of energies. Now, let us increase the intensity again. Although you increase the intensity, it is behaving like a particle according to you, okay? Then the number of electrons will be remain same, any number of electrons will be increased. Why? 1 to 1 only, na? There should not be any increase in the number of here this is the problem. What experimentally they found? If intensity is increased, the number of photoelectrons increased. What is this? Once you decide it is a particle, no matter whether you increase the intensity or does not increase the intensity, it is a 1 to 1 interaction. That's why the number of electrons emitted will be fixed. But what experimentally they found? If you increase the intensity of the light, number of electrons will be increased. What is this? Then they explain, Aya, while it is hitting, it is giving the discrete amount of energies. After hitting, or while it is hitting, it is giving discrete amount of energies, but it is having probability distribution. Whose probability distribution? Light, photons. That probability distribution behaves like a wave. See how they will get ideas whenever there is a problem. To explain that, they are thinking one point, and again problem came, again what they are saying? It is striking the target and giving the discrete amount of energies, but its distribution behaves like a wave. This is what they explained. After that, Einstein term came. So one more time, let me finish this. Wait a minute. So if you increase the intensity, no change in the number of electrons emitted. Number of electrons emitted. But contradiction again. What is the contradiction? What is the contradiction? Number of electrons emitted is proportional to. That's good. Proportional అని చెప్పలేంలే కానీ increases అని రాద్దాం. As intensity increases, the symbol is increases, the number of electrons emitted also increases. Then how they are explaining this? They are explaining they are hitting the target and giving the discrete amount of energies. Their job done, over. After that, they are distributing like a wave. Probability distribution is like a wave. So if you observe carefully, if you assume light is only wave, only behaving like a wave, then what is the contradiction we got? Intensity, kinetic energy of the electron. Say yes or no? So if you assume light is behaving like a particle only, then what is the contradiction we got? Number of electrons. If you assume it is only wave, you got kinetic energy of electron, contradiction. If you assume it is a particle, number of electrons, contradiction. Now what Einstein did? What do you think? His genius. He combined both and published a paper. What they said, till then what they are thinking, what they are saying is light, they either they are thinking like a wave or they are thinking like a particle. But this fellow did, he combined both. He just combined wave nature as well as particle nature and called wave packet. Quanta, photon, that's it. But name is given by somebody else. Photon name is given by somebody else. So I hope you understand what I explained till now. This much is not required. Simply if I can give the formula, I leave the class. But you should know. The people at the time, they are thinking differently, a different way. Some people are thinking in a wave nature way and some people are thinking in a particle. And this fellow combined both. So what he did, so here, listen one more time. So finally, a photon or light, I hope you understand here what I am explaining. If you assume light as a wave only, so what is the contradiction we got? Violates the observation of kinetic energy of electron. Good. Try to understand slow. And if you assume as a particle only, okay, then it violates the number of, it violates the observation of number of electrons emitted. So, and he combined this wave and this particle, okay, right? He combined both. So just combined both and he made it wave plus particle together. It's a wave packet. That's why in school you studied light is a form of packets of energy. So what is that packet meaning? That packet is nothing but what is this wave packet. So light is not coming like a pure wave, not like a pure particle. It's a mixed behavior. It's a mixed behavior of both particle as well as a wave. And we can't separate them also. So it's wish. Whenever it wants to behave as a wave, it will behave. Whenever it wants to behave like a particle, it will behave. It's impossible to identify whether it is behaving like a wave or particle. If you are observing means what? You are disturbing the system. Once you disturb the system, the result will be changing. That's the quantum mechanics. Once you have done a measurement in the quantum mechanics, the system state will be collapsed. Say yes or no? Yes, I will tell you a small example. If you are classical particles, if you are all classical particles. Say yes or no? Yes. Right. Now the doors are closed. There is no light passing through this. Okay. Now I want to observe one person location. Okay. Then I enter into this classroom. What I will do? I will take the torchlight. I will search. Say yes or no? Yes. If I focus on you, are you going to change the place from that bench to another bench? Why? You are classical. Let us say you are all electrons. Assume you are sitting on the energy level, in the energy levels. Now I am doing the observation. I am going to observe where that electron is sitting. Then what I will do? I will focus the light. Then light falls on the electron. Then electron will absorb. And where it will go? So that's quantum measurement always disturb the system. Classical measurement won't disturb. The quantum measurement is, once you measure, the system is collapsed. Because whatever the result you are getting, it will be in that state only. I will tell you one more. Do you have 1 rupee coin? 1 rupees coins leva ee madhya. Okay, anta okay. Sir, anyhow, so let us suppose you flip the coin like this. Okay, flip the coin like this, right? So what is the result? Huh? Head, అది classical. Then what is quantum? Both. Don't know కాదు, both. So it's a both. That means it can be available in both the states. So once you open and once you observe, it is collapsed to one state. Say yes or no? Till you didn't observe, till you didn't observe, this is in the superposition of head and tail. Once you open and seen, it's collapsed to single state. And until you observe, till you observe, the quantum system remains same. Once the observation is made, it's collapsed. But a classical state is not like that. Okay, anyhow. So finally, I hope you understand what I want to convey to you. So how Einstein got the idea of both. So he just combined both the ideas of wave and light. Because see, if you observe carefully, while it is hitting the target, it behaves like a particle. And after hitting, it is a distribution like a wave. That's the two different ways it is behaving. And he combined both, and now light is behaving like a, or light is absorbed by the particles like a wave packets of energy. What is this energy? H in it. So this is called wave packet. So this packet is having a minimum energy, how much? H. So this packet of energy is absorbed by one electron, and one electron is coming like that. And it is having amplitude changes. So what is the meaning of this amplitude changes? Probability distribution. Yes. So because the number of electrons should be increased. So it is having both discrete nature of this energy as well as probability distribution of wave. So that's why light behaves like a and after Einstein published the paper photoelectric effect, still one person fighted. Who is that? Millikan. Millikan was not ready to accept this, and he did his own experiment. He he is having his own lab and he will do so many experiments. I think you know Millikan oil drop experiment. Okay, so that Millikan oil drop experiment. What is that Millikan oil drop experiment? Finding the specific charge of the electron. So do you know how difficult it is? How accurate? And the whole credit goes to that great person, that Planck's constant value. He measured all these things. Okay, so great person. That Millikan oil drop experiment, specific charge of the electron, that is a 4 hours experiment. How many hours? 4 hours. He used to stand 4 hours in the lab. Daily 4 times he did because of forgetting accuracy. So can you stand 16 hours in a lab? In the lab? Huh? Impossible. If you say, sir is asking to stand 16 hours and work, come beta, come back. No need to stay there. So those people are all, they sacrificed their lives to your physics. Okay, and that woman, I hope I told you already, she sold out all her properties and established the lab because there was no one is ready to invest those things. So they take an initiative, and all these are great people. And I want to come out of this, and I want to make one statement. What is that? Yeah, please take this. All right. So I hope you have completed. So wait.